So often you want to actually have a look at, have some sort of relation corresponding to the actual coordinate, the axis in your domain. So we have this function called the coord function, which simply returns the coordinate. Right, so what I want to do now is basically just construct a linear solution, the analytic solution, sorry, for our temperature solution that we just created. It's just a basically straightforward linear function. And the way we do that is analytic solution. So I think what we want is 1 point minus. Right, so we need to create the coord function. And then once we've created it, we want to grab a particular index of it. In this case, we want to grab this index here. All right. So let's just check that that's actually doing what we expect it to. So we're going to render it over the mesh, and then, like I mentioned before, this object always expects a function that can be any type of function. In this case, it's not a function that uses any. It's a purely continuous function. It doesn't use any of our discontinuous data. Let's see how we go there. Right. I'm going to pop that in there. So let's see it. So just to reiterate here, we create the coordinate function. We grab the y coordinate off that guy, and that's it. Now what I wanted to do, let me just come back a few steps here because we've modified our temperature solution, and let me just regenerate that. So just step back, hit solve again, and then we can go forward again. Let me just confirm that this is no longer. Yep. Right, so what I wanted to look at was a difference of our analytic solution and our actual solution. So let's go let's grab the absolute value of those guys and go analytic solution, and then we just subtract our temperature solution from our finite element method. Now let's have a look at this. Right, here's the error of your solution. As you can see, these numbers are small. We've got down to 10 to the minus 6 here. The actual form of these errors is probably in some way related to, might be related to the actual method we've used to solve the linear system of equations. Right, so the other thing you obviously are going to want to do a lot of the time is actually access your data. Now we've seen how we can do that directly via the NumPy arrays, but what happens when you want to actually access your data in an arbitrary location in the domain? All right. Now we're going to use the evaluate method for that. So in the case of your temperature field, when you call evaluate, it will actually find the location where you're evaluating, like find which element that point is in, and then it will use your shape functions to construct an interpolation and arrive at a value at that position. So we can just pass it directly a coordinate. So let's say we've got temperature, and then like I mentioned, temperature fields themselves are functions. The mesh variables themselves are functions, so we can directly call evaluate on it. Let's pass in any position. Let's you pass in just a coordinate here, 0.5, 0.5, say, and then it returns the solution at that point. Likewise, instead of passing in one coordinate, you can pass in an array. So let's create an array called coord. Let's just go, let's say we want to get 10 points. I think we had it somewhere. Right, so we want a coordinate array of counts. So we want 10 positions, and they're two-dimensional position coordinates. Right. Now, I think we can use a NumPy linear space object or method to create a list of points from 0 to 1. So let's see how that goes. Space. We want to go from 0 point to 1 point, and we want to go over 10 points. Now, we originally just created an array of 0, so let's start filling in those the numbers, the coordinates we actually want to use. Let's grab all of them, and we want to just grab a set of points through the center of the domain. So let's set the x coordinate is equal to 0.5, and we will set the y coordinate equal to this linear space guy we've just used. Right, so if that all worked, we should just be able to now just do a temperature variable dot evaluate, and we pass in that entire array here, and there we go. So in this case, it's gone ahead and done your interpolation at all those points and return the values again as a NumPy array.
So does this have to go through all cells and then on each cell find what that is?
It uses an algorithm to walk through the mesh to find out, because it does need to find which element it lives in. So for each point, it will. I think actually, if your mesh is strictly Cartesian and regular geometrically, we leverage that to just find exactly. Well, we can find almost immediately. All right, you must be in this element. If your mesh is deformed, then we need to use some sort of algorithm which walk through the mesh to try and find which element it lives in.
So that might be really expensive.
It can certainly be expensive, yeah, definitely. The way the functions are set up, obviously, if you're asking for arbitrary coordinates, it's going to somehow it has to find which element it lives in. However, the way we've set up the functions are that wherever possible, it leverages the information it has at hand to try and do things as efficiently as possible. So, for instance, if you pass in, you can actually pass in. So, you can pass in actually. I'm not going to really talk about this today too much, but you can pass in the mesh object itself into any function. Then we'll actually walk through the mesh and evaluate those functions at those coordinates, but it'll actually use that node information, so it doesn't actually have to go, find a global location, then do the whole walking thing. But that will return the values across the entire domain. So, of course, we can also evaluate our analytic solution at those points as well. Okay, let's plot those using Matplotlib. So, whenever you want to use Matplotlib in your notebooks with Underworld, we have this little function we've created. In notebooks, you normally use what they call a magic to inline the results. So basically, it will actually draw the result in your notebook. But we've created our own custom one, which is basically just more parallel friendly, because if you use the native one that Jupyter notebooks provide for that, it doesn't play nice as soon as you want to do things directly in Python. Right. Okay. Sorry about that warning. So, it's just as simple as plot. So we're going to plot across the coordinates. Now we just want to grab the y coordinates for that, and we're going to plot again just the differences. All right. So actually, what I'll do is step back. Let's actually store those as Fem solution. Alright. Wow. Alright. And now we can do we call this analytic data. Come on, autocomplete. Analytic data. Now this is not what I was expecting to see. It's because we wanted to grab the y coordinates. Right. That's just a quick demo of how you can use Matplotlib to actually, plot your various analytics and keep everything in one place in your notebooks. All right, time for you guys to have another play now. Create a new notebook. Create a mesh and a temperature mesh variable. Set up boundary conditions. I want to try and set up a thermal conductivity of this form here. All right. Go ahead and set up your steady state heat, and as a bonus, have a play with the exception functions to ensure that you always have a non-negative conductivity.